Well, hello there folks, I hope you're doing well. In this video, we're going to be talking about the rest of the examples in section 10.2, area between curves. So we're going to be starting with example number 2, and that is found on page 457 of your textbook. So example 2 asks us to find the area of the region bounded by the parabolas y is equal to x squared and y is equal to 2x minus 2. So we got y is equal to x squared and y is equal to 2x minus x squared. So the first thing that we need to do, of course, is to determine where these curves intersect so we can figure out what our bounding x values are going to be. You could, of course, draw this out, but since you have a fancy-dancy graphing calculator, let's just use the calculator instead. So I will actually plot x squared is y1 and 2x minus x squared is y2, and I could just graph this and it would show up and it would look fine. But there's actually a little feature that I want to show you. So it's in the draw menu. This might be different on your calculators. Of course, this is the TI-83 Plus, but there should be something similar on those fancy TI calculators, of course. It'll be much more impressive. But anyway, so I go second program, which is the draw function, and I go to the seventh option, which is shade. What I do here, actually, I think on your calculators, you actually get to just choose. So you just choose y1 and y2. On mine, I have to specify that. And so the way that I specify that, and in case you have to as well, I go to vars, which is the variables, go over to the y vars and choose function and y1. And then I hit comma, and do the same thing and choose y2, and I close my bracket. I could have also put in my function. I could have put in x squared, comma, 2x minus x squared, close bracket. Either way it works, but then when I hit enter, it should draw it for me. And there we go, and it shades it in. So I'm looking for a point. Even just looking at this, I can see that my 2 points are going to be x equals 0 and x equals 1. So it's, totally a possibility to do it that way, but just to be sure, I really should calculate the intersection. So I will, that's the first curve, that's my second curve. I guess, hopefully it's possible to see over there, so I guess with the shading, it's kind of hard to see. It makes it a little trickier. Yes, it is 0, 0, and then I'll calculate the other intersection. Make sure that I'm on the right curves. First curve, second curve, and guess way over at the other side, and I don't think it's going to be any surprise. No, it's 1, 1. Okay, so those are my two boundaries that I need to deal with. With that now, I'm ready to solve my equation. So this intersection here is, the value, or the function, sorry, the total function together now, knowing that, so 0, 0, 1, 1 are my two important parts. So for y is equal to 2x minus x squared, when we're looking at our function again, that's going to be the top boundary, and then the x squared is going to be the bottom boundary. And so maybe that's another benefit of drawing it separately. We could have actually looked at it to see what it was going to be before we drew the shading. So the second function, the 2x minus x squared, is going to be our top boundary. We take the 2x minus x squared is going to be first. So for our combined function, the derivative of the area is going to be 2x minus x squared. And then we subtract our second function, which in this case is just a plain old x squared. So our combined area function, derivative of the area function, is 2x minus 2x squared. And now to find the area function, we need to find the antiderivative. So the antiderivative is going to equal, sorry, I should use f, not a, because those are slightly different things. So f at x is going to be equal to, well, the antiderivative of 2x is simply x squared. And the antiderivative of negative 2x squared is negative 2x cubed over 3. And then, I mean, we could do it the other way where we add c, but we're not going to do it that way. We're going to do it the other way. I already called it the other way. We could have used the way where we solve for c and use that function, but instead we'll just use the second way that we learned earlier in this chapter, where we just subtract the end boundary's antiderivative from the beginning's boundary antiderivative and make RC equal 0. So we'll leave it at this. What I'm trying to say is we're going to leave that at this, and then know that the area when x is equal to 1, which of course is one of our important values, is equal to the antiderivative at 1 minus the antiderivative at 0.0, which is our other boundary. The antiderivative at 0.1, so that's equal to 1 squared minus 2 over 3 times 1 cubed, which is, or let me just, I'll simplify after, minus 0, because I have 0 squared minus blah, 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 blah. So that's the same as 1 minus 2/3, which gives us an area of 1/3. So the area under the curve, or sorry, between the two functions, is equal to 1/3. And once again, at this step, I could have put my classic plus c and solved for c when f is equal to 0, and that would have worked. I'm not sure what mistake I made when we were in class. I just double checked it before I started recording this video, and it does work the other way. I just made a silly mistake somewhere. Yeah, and so that's it. Our answer 1/3. That's the answer for example number 2. For example number 3, it's a little more complex. Find the area of the region between the curves y is equal to sine x and y is equal to cos x from 0 to 2 over pi. So, I guess first thing that we want to do is switch the calculator back on because it just went to sleep. I switch the calculator back on, going to clear my drawing, so I go second draw 1, that clears drawing. And then I'm just left with my graphs. Clear my graphs because I am interested in the intersection of sine x and cos x. So the first thing I am going to do is put in my sine x and take a look at the graph. Oh, you know what? I need to change my window, or let's change the zoom to trigonometry. So 7, the Z trig. Maybe not quite what we're looking for right now, but it's a good start. I'll change my zooming in a minute. So, of course, sine x starts at the bottom, and then goes up to 1, and goes down to 1, and crosses over the x-axis at pi over, or sorry, at pi. For cosine x, do the same thing. And you know what? Let's just zoom in a little bit further to get a better look at. And you know what? I'll just change my window settings instead. Oh, it's in degree mode. That's what's going on. So the first thing I should have done is change it into radian mode because we are dealing with radians here. So I'll regraph it. Nope. Need to re-zoom it. Oh my goodness. We'll get this done here. Okay. Rezoom it. Zoom trig. There we go. So there's my sine function. There's my cosine function following after. And now I'm going to change my window mode. It's just, we don't really need much of the outside, so maybe negative pi over 6, just to get a good look at it for our x min. Our x max, we're only carrying up to pi over 2, so maybe we'll go up to 2 pi over 3. And of course, if you're comfortable without doing all of this, go for it. Who am I to tell you what to do? And we only care, let's say, negative 1.5 and positive 1.5. And that should give a much more zoomed in picture with the stuff that we are interested in. However, I will change the scale, because the intersection happens right between pi over 2 and 0, which is going to make it pi over 4. So I will change my x scale to pi over 4. And that should get everything looking all nice, just like it does kind of in the picture right there. Now the issue with this one is that since we're interested in the in the area between the two graphs across this whole function, we have to actually do it in two pieces, because in the first part, cosine is above the sine graph, but in the second part, after pi over 4, suddenly the sine half is over the cosine half. So we have to split this into two functions, because I mean, if I show you just the draw function, this probably won't look very good. So if I shade, why don't I just put that in again? So it all looks good, and then it's broken, because suddenly it can't shade anymore. Suddenly there's nothing there. So to see the other half, I'd have to actually put in the opposite. So if I quit now and have it do the same thing, so I'll do y2, and then my first one was sine x. I'm just mixing it up here. Instead of going into my menus and choosing y2, this I think maybe will work. No, it doesn't even work. Didn't work. That's fine. That's fine. Either way, this fancy shading is maybe more trouble than it's worth in this case here. So what I am going to do now is do it into two parts. Yeah, okay, it didn't work. I must have messed it up somehow. The important thing is finding out where this intersection is. We already know it's pi over 4 because I've mentioned it's pi over 4. But just in case I didn't know, I want to double check. Where is the intersection of these two lines? Point 78539816. Which, if we look at our window, is the same as pi over 4. If you want to do it mathematically, what you can do is, I'm looking for the point where cosine x is equal to sine x. And my domain, I only care when x is between 0 and pi over 2. There we go. Sorry about that. We only care when it's between those 2 points. And so when you solve for that, you could divide both sides by cosine, and I'd say 1 is equal to tan x. So if I divide both sides by cosine x, then have sine over cosine, which of course is tan, and tan x is equal to 1 at pi over 4. Well, the first time it's equal to 1, and the only time in our domain is when x is equal to pi over 4. But, I mean, use your calculator. Use the tools you have to figure it out. Use the internet, whatever it is. So the point of intersection is that x is equal to pi over 4. What is the point of this? Well, that means for the first half, I have the function, I have my cosine minus my sine. But for my second half, I have sine minus cosine. Because on the second half, my sine is above my cosine. And so I have to have the sine first. But in the first half, the cosine is first. So that's where I'm getting that from. And so I have to find the antiderivative twice. Luckily, the antiderivative of these functions are not too bad. So the antiderivative of the first one, well, the antiderivative of cosine x is sine x. And the antiderivative of negative sine x is positive cos x. And for our second half, we have something similar. So pardon me, the antiderivative of sine x is negative cos x, and the antiderivative of negative cos x is negative sine x. So the first half is from 0 to pi over 4, and the second half is from pi over 4 to 1. And so I now have to do those two parts. So first, my first part, my area is going to be equal to, so my area at pi over 4 is equal to the antiderivative at pi over 4, the first antiderivative at pi over 4, minus the first antiderivative at 0, which gives me sine at pi over 4 plus cosine of pi over 4 at pi over 4 minus sine of 0 plus cosine of 0, which is equal to, so sine at pi over 4 is equal to 1 root 2 or root 2 over 2, whichever way you prefer. So 1 over root 2, and sine of 0 is 0, and cos at 0 is 1. So that's minus 0 plus 1. So that is the same as 2 over root 2 minus 1. But if I rationalize the denominator, if I multiply both sides by the top and the bottom by root 2, so if I multiply this by root 2 over root 2, root 2 times root 2 is 2. So I have 2 over 2 times root 2 over 2, which simplifies to 2 root 2. Pardon me, no, just plain old root 2. Which simplifies because 2 divided by 2 is 1. Hopefully that makes sense. So I have root 2 minus 1. So that's only for the first half. For the second half, I'm going to do something similar, but it's the area at pi over 2, which is equal to my second function at pi over 2. And they put little marks there to differentiate between them, so maybe let's do that as well. Minus, since the pi over 4 shows up in both of them, we have to be careful not to do the wrong one. So I now have function 2 at pi over 2, so that's negative cosine at pi over 2 minus sine at pi over 2. Don't know why I put that one in brackets. Minus, in brackets once again, negative cosine at pi over 4 minus sine at pi over 4. Which, I mean, I guess is a little messy. It's a little messier than last time. But pi over 2, of course, is an important point on our graph because at pi over 2, the value of cosine is equal to 0. And sine of pi over 2 is 1, so it's 0 minus 1. Minus negative cosine of pi over 4. Well, cosine of pi over 4 is still 1 over root 2, so it's negative 1 over root 2. Minus 1 over root 2, which simplifies to negative 1 plus 2 over root 2, which we've already determined is equal to root 2. So that's the same as root 2 plus 1. Or, pardon me, root 2 minus 1. So we have root 2 minus 1. Sorry, that got slightly cut off. Let me move everything over so it'll fit. There we go. Beauty. So we have root 2 minus 1 for the second half. And root 2 minus 1 for the first half. Which means I just add these two together. So to add them together, it's pretty easy. Total area is the area of the first half, root 2 minus 1, plus the area of the second half, root 2 minus 1, which is equal to 2 root 2 minus 2. So the area underneath the graph, after all that work, we find that the area, or between the two graphs, is equal to 2 root 2 minus 2. That may have been a tricky equation, but I hope you were able to follow along. And if you have any questions, of course, please do ask me. But we still got one more example, so don't go anywhere. Example number 4 is actually kind of a simpler example. The one thing, though, is that it deals with a curve that goes under the line, so let's check that one out. Find the area between y equals negative sine x and the x-axis from pi over 6 to pi over 2. So just to get a look at it, well, you know what? That's easy enough. So basically, the x-axis is working as our top. So, yeah, I mean, I'll sketch it out just quickly. So let's clear this drawing first of all. And there is a way to, I think I mentioned this already, but there is a way to actually limit the boundaries of the drawing, but I mean that's beyond the scope of this right now. I can totally let you know if it's something you're interested in, but maybe it's more trouble than it's worth. So I will just put in a good old negative right there and clear that. And what are we? Perfect. Okay. But I should switch it to pi over 6. Table set to pi over 6. No, table set. Window set. My scale, instead of being pi over 4, let's make it pi over 6. Which, there we go. So we're just interested from pi over 6 to pi over 2. 3 pi over 6. So these, between the first tick and the third tick, is going to be our shaded area. And yeah, so let's get started with that. If my computer wants to behave, there we go. Oh, boy, that's not quite a straight line. Nope. Well, We'll just pretend. Just like school and the whiteboard. You know what, that should be more in the middle. This is a sine function. So the negative sine function is going to look something like that. And we only care about this part here, which corresponds to pi over 2. And this first part here, this corresponds to pi over 6, not perfectly to scale, obviously. So we do exactly the same thing. We have two boundaries. We have y is equal to 0, because 0 here, that's going to be our top boundary, so it's just going to go straight like that. And our second boundary is y is equal to negative sine x. Since the y equals 0 is on top, when we put it together into the one equation, we are interested in the derivative of 0 minus negative sine x. Or in other words, just plain old sine x. So the antiderivative of negative sine x is, of course, the derivative of sine x, antiderivative of sine x, I'll get it right eventually here, is just plain old negative cosine of x. And so to find out what we need to, what our answer is, the area at pi over 2 is equal to the antiderivative at pi over 2 minus the antiderivative at pi over 6. That is a 6. So that is equal to negative cosine pi over 2. Like I said, this is an easier one. Minus negative cosine pi over 6, which of course becomes a plus. And so cosine of pi over 2 is 0, because that is where the cosine function crosses the x-axis, so that's just plain old 0. And the cosine of pi over 6, if I cheat and look at the book because I don't remember my ratios anymore, is root 3 over 2. So the area at pi over 2, or between pi over 2 and pi over 6, if you want to call it that, is simply root 3 over 2. That's our answer. Easy enough to do. And because this is perfectly reflected in the x-axis, since it's just negative sine x, we could have used positive sine x and we would have gotten the same answer, because positive sine x is going to have the exact same area between these 2 points. Obviously, I did not draw it to scale, but this area on top is going to be identical to the flipped area on the bottom. And that's it. That's chapter 10.2, the area between curves. Hope this was clear. If you have any questions, please do let me know. I hope you have a fantastic day, and I will talk to you later.